video, we are going to learn what is the Fourier series of the periodic function. Suppose we have a periodic function defined in the interval a to b. The Fourier series of that periodic function can be written with the help of this form, that is a0 by 2 plus summation starts from 1 to infinity an cos of 2n pi x by b minus a plus summation n from 1 to infinity bn sine of 2n pi x by b minus a, where a0, an and bn are called as a Fourier coefficient. Now if you expand this one, what we have a0 by 2 plus, take n is equal to 1 over here, so we have a1 cos of 2 pi x by b minus a plus n is equal to 2, that is a2 cos of, that is 2 times of 2, 4 pi x by b minus a. Next term is a3, because n is equal to 3, a3 cos of 6 pi x by b minus a. So this sum continue till infinite terms, plus if you expand this one, we have b1 sine of 2 pi x by b minus a plus b2 sine of, take n is equal to 2, we have 4 pi x by b minus a plus, take n is equal to 3, b3 sine of 6 pi x upon b minus a. And again the sum continue till infinite terms. So this is how we need to find the Fourier series. Now the point is, it is very difficult to find a0, a1, a2, a3, b1, b2, b3 as a individual terms, but we have a general formula in order to calculate a0, an and bn. Here we can observe that in a0, an and bn, one term is common, that is 2 upon b minus a. And moreover, they have an integral from interval a to b. In the a0, we have a function. In an, we have a function into cos of 2n pi x by b minus a. And in case of bn, we have function into sine 2n pi x by b minus a. Even we can find the value of a0 with the help of an. If you substitute n is equal to 0, we have cos 0 is 1. So we are evaluating a0 separately. Also, if you observe from the Fourier series, with an we have the cos term and with bn we have sine term. As well as in an integral, with an we are taking a function into cos term and in bn function into sine term. Now let's learn how to find the Fourier series for the given function. The first question is, find the Fourier series to represent this function from the interval minus pi to pi, and hence find this expression from the obtained Fourier series. So what we need to do, so first we will write the function. In this case the function is equal to x minus x square. Then observe the interval. So as per this one, the value of a is equal to minus pi and the value of b is pi. Now what is the length of the interval? That is b minus a, that is equal to pi minus pi, that is equal to 2 pi. Now write the Fourier series formula. So Fourier series formula, fx is equal to a0 by 2 plus summation n from 1 to infinity an, and with an we are taking the term as a cos 2n pi x by b minus a plus summation n from 1 to infinity bn sine of same angle, that is 2n pi x divided by b minus a. Now the value of b minus a in this case is 2 pi. So we replace this quantity as 2 pi, and same in this case. Simplify this. So we have a naught by 2 plus summation n from 1 to infinity a n, and the angle of cos is, that is n into x, plus summation n from 1 to infinity bn, and over here 2 is get cancelled with 2 and pi with pi, so we have sine n into x. Now we need to evaluate a naught, an and bn, and these are called as a Fourier coefficient. So a naught is calculated as 2 upon b minus a integration from a to b of the function fx with respect to x. So 2 upon b minus a is 2 pi, integration from minus pi to pi. Function value is x minus x square. Take its integration with respect to x. We have this quantity is equal to 1 by pi integration of x minus x square, that is x square by 2 minus x cube by 3, and the limits are minus pi to pi. Now substitute the upper limit and lower limit. So we have 1 upon pi, that is as it is. When you substitute upper limit, it is a pi square by 2 minus pi cube by 3, that is the value of upper limit, minus lower limit. So minus pi square by 2, this is the whole square, minus pi cube by 3. So this is equal to 1 upon pi square by 2 minus pi cube by 3 minus, simplify this is the pi square by 2, and here minus pi cube is negative times of pi cube, and negative is a positive. So we have this form. So this implies 1 upon pi square by 2 minus pi cube by 3 minus pi square by 2 minus plus is minus pi cube by 3. So from here, this term is get cancelled with this one. So we have 1 upon pi, and this term is equal to this one, but they are in a negative form. So we can write minus 2 times of pi cube by 3. Further simplify this pi is get cancelled with this one. So we have minus 2 pi square by 3. And this is the value of a naught. Now let's calculate the value of an. So that is calculated as 2 upon b minus a integration from a to b, that is minus pi to pi of the function fx into cos n into x dx. The value of b minus a is 2 pi. So we can write this as 2 upon 2 pi integration from minus pi to pi, and the function in this case is x minus x square cos of n into x dx. This is equal to 1 upon pi integration from minus pi to pi x minus x square cos of n into x. How to take the integration in this case? So both are the function of x, and in this case we will use the islet. For more details of this one, a link is given in the description. That is the first video regarding to the Fourier series, that is the foundation of Fourier series. A brief recap of that one. So we are going to use the islet. So according to this is the algebraic function and this is a trigonometric function. So a comes earlier than t, so this means this is the first function and this is the second function. So whenever we have a two function u and v, that is depending upon x, and where we have taken u as a first function and v as a second function, in this case the integration is evaluated as first function as it is, that is u is as it is, integration of v, that is v1, minus derivative of this term Then we will take the integration of v1, that is equal to v2, plus derivative of this term, second order derivative. Then take its further integration. Repeat this process until and unless we are not getting a derivative is equal to 0, and repeat this process with the alternative sign. In this case, how to apply this formula? So we can write this is 1 upon pi. First function is as it is, means x minus x squared. Integration of cos nx is sin n into x divided by coefficient of x, that is n, minus derivative of this term 1 minus 2x, integration of sin nx divided by n. So what is the integration of sin n into x divided by n? So n is not depending upon x, so we can keep it as it is. Integration of sin is minus cos nx divided by n. So we have in this case is minus cos of nx divided by n into n is n square. Then take the derivative of the next term, but with a positive sign, because alternative sign we need to take, that is positive, negative, positive. Its derivative is minus 2. Integration of this term with a negative sign as it is upon n square is as it is. Integration of cos nx is, that is sin n into x divided by coefficient of x, that is n. So already n square is there, so we can express this as n cube. Next term is minus derivative of 2 is, that is 0, so there is no need to take the next term. So we can bind this isolate over here. Now the limits are from minus pi to pi. Before moving to the next step, we will observe that what is the value of sin nx for both the limits, similarly for cos nx for both the limits. If any term is getting 0, we will not take that term in the next step in order to reduce the calculation. Like in this case, if you observe sin nx, if you take upper limit, means substitute x is equal to pi. So in this case, we have sin n pi. Sin n pi is always 0. And when you take lower limit, x is equal to minus pi. So it is a sin minus n pi. So we can write this as negative of sin n pi. Sin n pi is 0, minus of 0 is again 0. We will not take this term in the next step because it is getting a 0 for both the limits. Similarly, observe the behavior of cos function. So in this case, cos nx. So when we take x is equal to pi, so cos of n pi, that is equal to minus 1 raised to power n. And when we take x is equal to minus pi, so we have cos of n into minus pi. So this is equal to cos of n pi, because cos of minus theta is equal to cos theta. So we can write this is minus 1 raised to power n. So from here we know that sin nx at upper limit and lower limit is getting 0. So we can directly write this is equal to 0. Same for this, we have sin nx with the same angle. So again this is getting a 0 at upper limit as well as a lower limit. Final expression we have 1 upon pi, that is as it is. Minus minus is positive. So 1 minus 2x. This is cos of nx divided by n square. Upper limit is pi and the lower limit is minus pi. This is equal to 1 upon n square into pi, 1 minus 2x cos of n into x, minus pi to pi. Now substitute the limits. We have 1 upon n square pi, 1 minus 2 pi when you take upper limit, cos of n pi minus lower limit, that is 1 minus 2 times of minus pi cos of minus n pi. This is equal to 1 upon n square into pi 1 minus 2 pi cos of n pi minus this quantity is 1 plus 2 pi cos of minus theta is equal to cos theta, that is cos n pi in this case. So we have common term cos n pi, take this outside, cos of n pi divided by n square pi, the remaining term as 1 minus 2 pi minus 1 minus plus is minus 2 pi. Minus 1 and 1 will get cancelled. So finally we have, this is minus 4 pi by n square pi and cos n pi is minus 1 raised to power n. So we can write this is equal to minus 4 into minus 1 raised to power n by n square, because this pi is get cancelled with pi. This is also written as 4 times of minus 1 raised to power n plus 1 upon n square. In this case, the value of an is equal to this. Similarly, calculate the value of bn, that is 2 upon b minus a, that is 2 pi. Integration from a to b, that is minus pi to pi fx, rather than cos, it is now sin n into x dx. So 2 is get cancelled with 2. We have 1 upon pi minus pi to pi. The function of value in this case is x minus x square sin nx dx. Again, this is the algebraic function and this is a trigonometric, and a comes earlier than the trigonometric in isolate. So we are choosing this as a first function and this is as a second function. Now apply the isolate in this case. When you apply the isolate, first function is as it is. Integration of sin nx is, that is minus cos nx by n. Then this is the positive sign. Now take it as a negative sign. Derivative of this term is 1 minus 2x. This minus as it is, 1n as it is. Integration of cos nx is positive sin x divided by n. So negative sign, that is as it is, that n into n get converted into the n square. Next term is a positive. Derivative of this term is minus 2. Integration of this term, whole term. Integration of sin nx is minus cos nx. That negative sign into negative sign is a positive. Cos nx divided by the coefficient of x, that is n. So already n square is there. So here we have n cube. Upper limit is pi and lower limit is minus pi. Before substituting the upper limit and lower limit, again observe the cos function as sine function. Cos at n pi, when you substitute upper limit, that is equal to minus 1 raised to power n. Whereas sine n pi, when you put x is equal to pi over here, it is 0. Now for the lower limit, cos of minus n pi, that is cos of n pi, and we have minus 1 raised to power n. And in the case of sine minus n pi, so this is equal to minus sine of n pi, and sine n pi is 0. So negative of 0 is again 0. So it means sine function at upper limit as well as a lower limit is getting a 0. We will take this quantity as a 0 and we will not write this one in the next step. So finally we have 1 upon pi as it is. This minus outside 1 upon n, x minus x square cos nx, and here we have minus 2 cos nx divided by n cube. Now substitute the upper limit as well as the lower limit. So we have 1 upon pi. This is the value of upper limit. So x is replaced by pi, and even over here and over here, minus lower limit. So minus 1 by n as it is. X is replaced by minus pi minus x square means minus pi square is that is pi square, and this negative sign is as it is. Cos of minus n pi minus twice of cos of minus n pi divided by n cube, that is your lower limit. So in the next step we know that cos of minus n pi is cos n pi. So we can take cos n pi from here as well as from here cos n pi outside. Even these two terms contain cos n pi. So we can take cos n pi outside. So we have cos n pi divided by pi. Remaining terms are minus 1 by n into pi minus pi square. This is minus 2 upon n cube. Minus minus is plus 1 by n minus pi square, and here minus minus is plus 2 by n cube. This term is get cancelled with this one. Simplify this. This is equal to minus 1 raised to power n upon pi, and in this case minus pi by n. This is minus minus plus pi square by n, and in this case minus pi by n and minus pi square by n. Again this term is get cancelled with this one. Finally we have minus 1 raised to power n by pi minus pi by n minus pi by n minus 2 pi by n. This is equal to minus 1 raised to power n into minus 2. That pi is get cancelled with pi divided by n. We can further write it as twice of minus 1 raised to power n plus 1 by n. We have clubbed this minus with this term. We are getting n plus 1 in this case. And this is the value of Bn. The final Fourier series of the function x minus x square from the interval minus pi to pi is of this form, where we have calculated the value of a naught as minus 2 by 3 pi square, and the value of an is 4 by n square minus 1 raised to power n plus 1. The value of Bn is 2 by n minus 1 raised to power n plus 1. Now substitute these Fourier coefficient over here. So final Fourier series we have in this case as minus 2 by 3 pi square, that is divided by 2, plus summation starts from 1 to infinity 4 by n square minus 1 raised to power n plus 1 into cos n into x plus summation starts from 1 to infinity 2 by n minus 1 raised to power n plus 1 into sine of nx, and here we have the final Fourier series of this function. Now we are going to check it from the graph how this function is the Fourier series of the given function x minus x square. As you can observe from the graph, this is the graph of the function x minus x square, where it is represented by the dotted lines in a green color, and this is the approximation of this function by the Fourier series with taking n is equal to 1. The domain we have taken over here as minus pi to pi. Now you can easily observe from here how the Fourier series is approximating this periodic function by increasing n. In the next step, we need to find this expression from the Fourier series. Now in this expression, if you observe that we have 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square. In the denominator, we have a square term. and they are increasing by 1. So we need to change n. How you will get this expression? So this expression can be obtained by varying n. So where we have n square, we need that term. So n square is not in this case, but we have n square in this term, and here we have n. Do we need 1 by 2, 1 by 3, 1 by 4? Because from this term, what we have, when you vary n, that is 2 by 1, then 2 by 2, then 2 by 3, then 2 by 4. And we don't need that term according to this expression. It means this term must be 0. For that, we need to choose the value of x for which it is getting a 0. Because this is a non-zero quantity, we can make this factor as a 0. And when we need to choose x, make sure that is a part of the interval. For what value of x this is getting a 0? From this interval, that is 0. So if I put x is equal to 0, check it whether we are getting this series or not. So when you take x is equal to 0, we have f of 0. This is equal to minus pi square by 3 plus summation n from 1 to infinity 4 by n square minus 1 raised to power n plus 1. Cos of 0 is 1 plus summation n from 1 to infinity 2 by n minus 1 raised to power n plus 1. Sin 0 is 0. 0 into something is 0 and its summation is also 0. So this is equal to f of 0. Now what is a function? Function is x minus x square. Substitute 0 over here. So 0 minus 0 square is 0. And this is minus pi square by 3. Now from here take 4 outside before expanding this expansion. Minus 1 raised to power n plus 1 by n square. Simplify this. From here we have this term we can take on the right hand side, that is a positive pi square by 3 is equal to 4 times of, expand this series. So when you take n is equal to 1, so minus 1 raised to power 1 plus 1, that is 2. So minus 1 square is 1 divided by 1 square. Next term is n is equal to 2. So minus 1 raised to power 2 plus 1, that is 3. So minus 1 raised to power 3 is minus 1 divided by 2 square. Next term, when you take n is equal to 3, so minus 1 raised to power 3 plus 1, that is 4. Minus 1 raised to power 4 is 1. So it is a positive 1 divided by 3 square. Now what is the next term? So if you observe that if we are taking odd number over here, it is getting a positive 1. And when we are taking n is equal to even, it is getting a minus 1. So the next quantity is even. So minus 1 divided by 4 square. Continue. Simplify this. This is equal to pi square by, take this term over here, it is a 12, is equal to 1 upon 1 square minus 1 upon 2 square plus 1 upon 3 square minus 1 upon 4 square plus so on. So finally, we are getting the expression as per requirement. Another application of the Fourier series is that with the help of this one, we can reduce many infinite series along with its values.